So today we're going to talk about isomers. So isomers are basically compounds that have the same chemical formula. So in other words, they have the same number of atoms of each element, but they're two different molecules. Now, this can occur in two different ways. We can have structural isomers in which the central atom is bound to different atoms, or stereoisomers in which the central atom is bound to the same atoms, but they have they're a different three-dimensional arrangement in space. Now, the structural isomers can then be broken down into either linkage isomers or coordination isomers. And the stereoisomers can be broken down into being either geometric isomers with no mirror image or optical isomers that do have a non-superimposable mirror image. The geometric isomers can further be broken down into cis-trans or FAC-mer. And we're going to discuss each one of these in detail. So let's start with the structural isomers. So again, these are often, these are called structural isomers, or they may be referred to as constitutional isomers. Again, these are compounds that have the identical number of atoms of each element, but the connections are different among the constituent atoms. So first, let's look at the linkage isomers. So the linkage isomers arise when a ligand can bond to the central metal atom through either of two different donor atoms. So the polyatomic ions that we've seen that can do that are the cyanide, in which it can bond to the lone pair on the carbon or on the nitrogen. We've seen it with thiocyanate, where it can bond to the lone pair on the sulfur or the nitrogen. And we've seen it with the nitrite ion, where it can bond to the lone pair on the nitrogen or on a lone pair on the single bound oxygen atom. So it'll be these three polyatomic ions that can form linkage isomers. So let's look at this. So here is one. So here we have a pentamine nitrito. Well, in this case, it's nitro, right? Because it's bound to the nitrogen, and then the cobalt 3. And in this case, it is the nitrogen acting as the donor atom. So it's the lone pair on the nitrogen forming the coordinate covalent bond with the cobalt. Now, the other linkage isomer it will be bound to the lone pair on the single bonded oxygen. And these two isomers generally have very different physical properties. So in this case, you can see the color of the two salts are different, even though the counter ion in this case is the same. The only difference is the nitrogen is bound to the cobalt in this isomer, and it's the oxygen bound to the cobalt in this isomer. So these are what we call linkage isomers. Next, we have coordination isomers. These are sometimes referred to as ionization isomers. And in this type of coordination compound, basically what happens is the ligand switches places with the counter ion to form two different isomers. So here's an example of that. So here we have the tetraamine bromo cobalt 3 complex ion, and it has a counter ion of the sulfate. And when you throw this into water, it's going to dissociate into the complex ion and the sulfate as the counter ion. And this solution is violet in color. Now, the coordination isomer, or the ionization isomer, is when the ligand and the counter ion switch place. So now the sulfate is making a coordinate covalent bond with the cobalt through one of the oxygens, the single bound oxygens, and now the bromine is the counter ion. And again, when you would throw these into water, they would dissociate into the complex ion and the bromine ion. And this solution is red in color. So these are coordination isomers. So basically a ligand, and it has to be an ion. So one of the ionic ligands are switching places with the counter ion. So these are coordination isomers. So these are the two different types of structural isomers, linkage isomers and coordination isomers. Next, let's switch to the stereoisomers. So these are compounds, again, they have identical chemical formulas. They have the same number of atoms of each element within the compound. In this case, though, the connections are all the same between the atoms, but it is the three-dimensional arrangement of those atoms in space that make them different. So we can break them down into geometric isomers. These are also often called distereomers. And these do not have mirror images of one another. And then we have the optical isomers, again, often referred to as enantiomers, and they do have mirror images of one another. So let's start with the geometric isomers. So a geometric isomer or distereoisomer are stereoisomers that are not mirror images of one another. They're not related through a reflection operation. So we have the square planar type molecule. So we have the central atom, and then we have two different types of ligands, and there's two of each. So here's an example of that. So we have the central platinum atom in this particular case, and then they're bound to two chlorides and also to two ammonias. The same thing is true here. They're bound to two chlorine and their chlorides and to two ammonias. But we'll see here that there's no way to rotate these two molecules, right? I can't rotate this in any way to get the same molecule. Otherwise, they wouldn't be isomers. They would be the same molecule. So first off, we can see that they are definitely isomers. All the connections are the same. The platinum is bound to two chlorines and two nitrogens. The platinum is bound to two chlorines and two nitrogens. So that makes them stereoisomers. Now, are they geometric isomers or optical isomers? Well, we can clearly see these are not mirror images of one another. So they must be geometric isomers. Now, if they're geometric isomers, we're going to further determine whether they are cis or trans isomers. So if they are on the same side of the central atom, we're going to call them cis. And if they are on opposite sides of the central atom, we're going to call these trans. So geometric isomers seldom have the same physical properties. So in this case, you can see this molecule, right? The dipole moments are not canceling. So this molecule is going to be polar. In this case, the dipole moments are canceling one another because they're equal and opposite for both of them. So this molecule would be nonpolar. And of course, polar and nonpolar molecules have extremely different physical properties and oftentimes chemical properties as well. Okay, let's look at another example. So this time we have this complex ion, so tetramine dichloro cobalt 3 ion, and we want to look at its geometrical isomers. So here's one example where we simply put the two chlorine on the same side of the central atom, therefore it would be cis. And again, these are going to have the formula where there's two different ligands, 4 of one and 2 of the other. So that way we're going to have the cis and trans. And then here's the other. I put them opposite one another from the central atom. And so this would be the trans isomer. So again, you can see they're not mirror images of one another. There's no way to rotate them to get the same molecule, because again, that would mean they were not isomers. And so again, all the same connections, therefore they are stereoisomers and specifically geometric isomers. On the same side, we call them cis. On the opposite side, we call them trans. Now, what if we drew this molecule? Okay, so this time I took this guy and I put him up here. The question is, are they isomers? Well, if we simply rotate this molecule, right, we rotate this down to this position, that's going to move each one of these to this. And basically, we are going to get the identical molecule. So these two molecules are the same molecule, and therefore they are not isomers. So that's what you got to worry about. If you can rotate them and they're the same, well, then they are not isomers of one another. They're the same molecule. Okay, let's look at another. So here's two other compounds. This time, these have the formula of the single metal, and then they have 3 ligands of one type and 3 ligands of another type, and they're octahedral in structure. So in this case, we can't name them cis and trans. We're going to have to go with FAC and MER. So in the case of the FAC, you'll notice that they are not in the same plane, right? These two are in this square planar structure right here. And then this is coming out of that plane. So they're not in the same plane. In this case, we could look at this square planar structure right here, and we can see that they're all in the same plane. So when they're in the same plane, we call that MER isomers. So this is our FAC and MER isomers. Next, let's look at the optical isomers. So these are oftentimes called enantiomers. And again, these are going to be stereoisomers, but this time they have non-superimposable mirror images of one another. So what does that look like? Well, first off, I want to say that two compounds that are optical isomers of each other have the same physical properties for the most part. This makes it bad, for example, in the pharmaceutical industry when they're trying to separate the isomers out of a mixture. So, for example, vitamin C has two isomers. The one we need to live, the other isomer will actually kill us. So, if the pharmaceutical industry is trying to produce this through a chemical process, they're going to end up with both isomers. So how do they separate the two isomers? Well, the physical properties are going to be the same because they're just mirror images of one another. So if one's polar, the other is going to be polar. They're going to have the same density. So you're not going to be, they're going to have the same boiling points and melting points. So you're not going to be able to, do fractional distillation where you heat it up and vaporize one off before the other. So it makes it very difficult. Now, the only physical difference is the fact that one isomer will actually rotate plane polarized light in one direction, and the other isomer will rotate that same light in the opposite direction. And I'll talk about that later. And so, like I said, they have substantially different biological effects. Okay, next let's talk about achiral and chiral. So an achiral object lacks what we call handedness. Basically, it has a plane of symmetry, right? So they're basically a mirror image from one side to the other. So if it has a plane of symmetry, we would say that that molecule is achiral. On the other hand, if it does not have a plane of symmetry, so in other words, I can't cut this hand in half, so it's a mirror image of the one side or the other, right? And I can't cut it off in the plane of the hand, right? Because one side would be the palm, the other side would be the back of the hand. So there's no plane of symmetry. Therefore, we would say that this is a chiral object or a chiral molecule. So it has no plane of symmetry and non-identical mirror images. And so we say that this has handedness, right? So in this case, this is the right hand, and obviously the left hand is a mirror image of the right hand, but it's not the same. There's no way to rotate it and get the same. So those would be considered optical isomers. So the left hand and the right hand would be optical isomers, and they're chiral because they don't have a plane of symmetry within each of the hands themselves. So let's look at a molecule. So let's look at this complex ion right here. So we could have a mirror image of this molecule, and it would look like this. Okay. So now you can see that, again, here's the central atom. We have this ethylene diamine bidentate ligand in the back, and so the mirror image of it would put it back here. In this case, we have the nitrogen coming up and then back down to one going back behind the board. So it's coming up from the top and then to the one going back behind the board. Here we have the one going down and then coming out to the one coming out to the right front of the board. And so the mirror image of that would be going down and again coming out to the right left of the board. So there's the mirror image. So these two would be optical isomers. You'll notice that there's no way to split these two molecules down the center, right? This side is not a mirror image of that. And if I try to slice it through this way, okay, this one's going back, but this one's coming forward. So again, they are not mirror images of one another. So there's no plane of symmetry, right? So these would be considered to be chiral molecules. Okay, so again, we have our left-handed and our right-handed molecules. Now, the question is, are these the same molecule? Can I rotate these, right? So what if I simply rotate this along this axis right here, 180 degrees, so that I put this ligand, the ethylene diamine, so that it's now over here, right, connected just like this. So that would be the same on that side. So when I did that, though, that's going to rotate this one. This was going to stay the same because we're rotating along this axis. And it's going to rotate it to this position here. Okay. Or is it? No, we went 180 degrees. So it's going to rotate it to this position here. So be careful when you're doing this. This is why you got to do your homework and make sure that you're looking at these, right? We went 180 degrees. So we went, right? We went 1, 2, right? So we went 180 degrees. So we're going to go 1, 2. So that puts this nitrogen connected to this nitrogen, but that's not the same as this one over here. So these are two different molecules. So be careful how you rotate these things. Again, please make sure you're doing your homework. Okay, and like I said, they do not have any symmetry. There's no way to cut them in half and have mirror images of one half to the other. So these are going to be chiral compounds. Okay, here's another example. This time all the ligands are the same. So obviously the mirror image of this would be identical to this molecule. So you wouldn't have an isomer for this molecule of any type. It does have a plane of symmetry, however. So since it has a plane of symmetry, it's going right down through the middle here, right? This is going to be an achiral compound. Okay, next let's talk about the optical properties of optical isomers. So a polarimeter is a device that measures the rotation of plane polarized light. So this is going to occur again for chiral compounds. So basically we have a light source, and this light source is simply putting out light that is in all planes, right? So it's in all different planes it's coming out, and we call that unpolarized light. Then it passes through a filter. This filter basically just has slits that are going up and down. So they're only allowing light with within that same plane to pass through. If they're not in the same plane, right, they're simply being blocked by the rest of the filter. So this is our filter, and it's called a polarizer. So now coming out, we have what we call plane polarized light. So it's all in the same plane, right? It's all in this plane going up and down. It's then going to pass through a cell that contains our solution with the chiral substance. Well, that chiral substance is actually going to cause this plane polarized light to rotate. So now we have the rotated plane polarized light coming out. Then we have another analyzing filter. It's just another polarizing filter like this. And so if it's in the same direction as the original polarization filter, you're going to see nothing. There's going to be no light coming through because the rotated polarized light is now being blocked by the filter itself. So what you have to do is you have to rotate the filter. Okay, you have to rotate the filter until you can see light coming through the filter. That's what we call the angle of rotation, and you can measure that for a specific compound. So every specific compound that's chiral it rotates plane polarized light by a different angle. And depending on if it is the left-handed or right-handed structure, it's going to rotate it clockwise or counterclockwise. So the right-handed would rotate it clockwise, the left-handed would rotate it counterclockwise. Now, if it's not a pure mixture, let's say it's 50-50, we're going to call that a racemic mixture, as we're going to see in the next slide. It's not going to rotate the light at all because half the molecules are going to rotate it a certain number of degrees to the counterclockwise, and the other half of the molecules are going to rotate it the same amount, but counterclockwise. So for a racemic mixture, you would see no rotation of the plane polarized light. But let's say it's a 25-75. Well, it's going to rotate the light proportional to that fraction of isomers. So optical isomers, again, can be identified by the specific angle with which they rotate plane polarized light. We're going to label optical isomers as either plus, minus, or sometimes R and L. In fact, there's other ways that optical isomers are actually denoted, as you'll learn in organic chemistry. A racemic mixture, like I said, contains a 1-to-1 ratio of both the plus and minus isomers. And finally, a racemic mixture has no effect on plane polarized light, again, because the isomers are basically canceling out the rotation of one another. Okay, that is the end of this chapter. Please make sure that you are doing all of your homework problems. And if you have any questions, please make sure that you're asking me in class or office hours. Okay, let's try number 36 from chapter 22. It says, draw all the structural isomers for this particular coordination compound or salt. It's an octahedral complex, and label each as either linkage isomers or coordination isomers. Okay, so first it says it's octahedral. So that means we're going to have to start with the octahedral structure. So we have our central chromium atom, and then we have one coming straight up and straight down all on the same plane. And then in this plane here, we're going to have that square planar structure. So that basically looks like this. Okay, so they're all 90 degrees apart from one another. And what we're going to do is we're going to take it and flip it up like this. So that then I'm going to draw like this. So here we have one going back behind the page, one coming out of the page, another one going back behind the page, and one coming out of the page. Now they're going to be isomers, so we're going to need two of these. So we'll just draw another one right here. So here's our chromium, one up, one down, one going back behind the page, one coming out of the page, one going back behind the page, and one coming out of the page. Okay, so first let's start with the linkage isomers. So we have the formula, we have 5 ammonia. So we're going to go 1, 2, 3, and I'm going to write these backwards since it is the nitrogen that is forming the coordinate covalent bonds with the metal. Then we have the nitrite ion. Now, the nitrite ion, we could draw it like this, NO2, and that would be one of them. Now, keep in mind this is an ion, right? And as we can see, the sulfate has a -2 charge, so that means the complex ion itself has a +2 charge. Okay, now let's draw the other linkage isomer. Well, remember with a linkage isomer, it is going to be a ligand in which you have 2 possible donor atoms. Now, because there's not enough atoms between the 2 donor atoms, remember you need 4 atoms between those lone pairs to create a bidentate or another polydentate ligand. This doesn't work for the nitrate since there's only 3 atoms between the lone pairs. So what we could do though is take the oxygen. Remember the nitrite ion looks like this, right? So it has the nitrogen and then oxygen on both sides. It has the lone pair, and then it has 3 sets of lone pair here. Remember, it too, of course, is an ion. And so we could basically switch between the lone pair on this nitrogen. That's what we showed here. And we could actually use the lone pair on the singly bound oxygen. Remember, the lone pairs on the double bond or triple bonded oxygens generally don't form coordinate covalent bonds. And if they do, they're very weak. So the other linkage isomer, we're going to choose, instead of the nitrogen being the donor atom, it'll be oxygen as the donor atom. So we could just draw that then like this. Okay, and then these, of course, would all remain the ammonias. And it too is a charged species. And so these then would represent the linkage isomers, right? So these would be our linkage isomers. So these 2 are our linkage isomers. And remember that the linkage isomers are what we call structural isomers. So these are both structural isomers, the linkage isomer and the coordination isomer. Of course, the structural isomers is when we don't have the same connections between atoms. So in this case, they're all bound to the nitrogen for the ammonia, but in one case, it's bound to the nitrogen. In another case, it's bound to an oxygen. So we don't have all the same bonds around the central atom. Otherwise, that would be a stereoisomer. Okay, so now remember, these are actually salts. So we actually have the SO4 2- that is the counter ion for these salts. Now, that brings us then to the coordination isomer. So for a coordination isomer, what happens is that the ligands actually exchange. So the ligand exchanges for the counter ion. Okay, so in that case, that's going to look like this. So again, we'll have our central chromium atom. We'll have one going back out of the page, one coming straight out. Whoops, one coming straight out of the page, one going back, one coming straight out. And then in the plane of the paper, we have one up and one down. And again, this would be our ammonias at each one of these connections. And now this time it is going to be the sulfate. Now the sulfate has a structure that looks like this. And so it is going to form a coordinate covalent bond with either one of these oxygens. Again, it's not going to form it with a double bonded oxygen. So I could just write that like this. So I'll just write SO4 like that. And now this case, since the counter ion here is going to be the nitrite, which has a -1 charge, that means this complex ion has a +1 charge. So these would represent our coordination isomers. This would, of course, have the formula of Cr, NH3, 5, NO2. That would be our cation, and then our anion is the sulfate. And in this case, it would be the chromium, again, 5 ammonia. This time the sulfate is a ligand. That is our cation, and then our anion would be the nitrite. Okay, next let's try number 38 from chapter 22. It says, which of the following complexes or complex ions can exist as geometric isomers? Draw the structures of each possible geometric isomer and label them as cis or trans or as FAC or MER. Okay, so let's look at this first one. It says it's tetrahedral. So if it is tetrahedral, that means it is going to have our central atom, in this case our iron. Then we're going to have one in the plane of the paper going up, one in the plane going down at an angle of 109.5 from the other. Then we're going to have one coming out of the paper. And again, this is 109 from the other two, 109.5 degrees from the other two, and one going back behind the paper, again at 109.5 degrees. And since we're talking about isomers, let's just start and draw our second structure real quick. Okay, we got one going back. Okay, so we have 2 chlorine. So let's make this a chlorine. Let's make this a chlorine. And then we have the NO2. Now, since the nitrogen is written first in the formula, that means that the nitrogen is the donor atom. So this will be NO2, and then I'll write O2N over here. So there are the isomers. So now we can switch either one of these. So let's say this is the chlorine, and then we'll switch these two here. So this is the nitrite, this is the chlorine, and this is the other nitrite. Now the question is, are these different molecules? So if you're able to rotate these in any way and they are the same, then of course they're not going to be different isomers. So we could actually do that by simply rotating this molecule along this axis and rotate this one to here. That'll put this guy here and this guy here, which is identical to this structure here. So these are the same molecule. So these are the same molecule because you can rotate them, and therefore they are not geometric isomers. Okay, next let's try 38C. So we have a ruthenium with 3 ammonia, each being monodentate, and the bromine mean monodentate, and there's 3 of them. So that means there's going to be 6 coordinate covalent bonds. And if we have 6 coordinate covalent bonds, that means we're going to have an octahedral structure. So again, we're going to draw that central atom, which will be our ruthenium. There'll be one up, one down, and then again in this plane, there's going to be 4, which are square planar, and we will represent that like this. And since again, we're talking about isomers, let's just draw the other structure real quick. Okay, so we have the 3 ammonia. So let's go 1, 2, 3. And then we have the 3 bromines. So 1, 2, 3. And now you got to be careful when you draw your next one. You want to make sure that they aren't identical. So what I'm going to do is I'm going to put the ammonia here, here, and here this time. And then the bromines will fill in these other spots. Okay. Okay, now we got to make sure that they're not the same. So I can see here that these 3 ammonia are actually in the same plane, right? This would be a T shape, and they'd all be in the same plane. In this case, I could see that these 3 ammonia are not in the same plane, right? We could say these 2 are in the same plane, but then this one's going back behind it. Or we could say these 2 are in the same plane and this one's coming out towards us. So they are not the same. Now, again, these are geometric isomers because in both of these cases, we've seen that all the connections are the same. The ruthenium is bound to the nitrogens on the ammonia and the bromines. Again, they're bound to the nitrogens on the ammonia and the bromines. So these are definitely stereoisomers. Now, they're not mirror images of one another. So therefore, they are not going to be optical isomers, but they are going to be geometric isomers. So these are geometric isomers. Okay, now the question is, are we going to label these as cis-trans or FAC-mer? Well, when we have a metal and then 3 ligands of one kind, 3 ligands of another, then it's going to have to be the FAC-mer. So the FAC is going to all be in different planes, and the mer is all going to be in the same plane. So here I can see that all 3 ammonia, like we said, that's T-shaped, these are all in the same plane. So this is going to be the mer isomer. And then these again are not in the same plane. So this is going to be the FAC isomer. Okay, let's look at these 2 structures here. Okay, so here I had the one. We'll consider the nitrites to be the red atoms and the chlorides to be the white. So basically what you see here is the 2 white are in the plane of the paper, and the 2 red ones, the nitrites, we have one coming out at 109.5, right? You can see that it's coming out of the plane at 109.5, and we have one going back at 109.5. Now, if I set it straight up and down like this, so this would be the chloride here on top, and then the chloride here, and then the 2 nitrites that we have there, okay? So that would be the one structure. Now, basically, if we had the same structure again, right? So if we had the same structure, basically what we did is we took and we switched the chloride and the nitrite, right? So we took and we switched the chloride and the nitrite. So there was the chloride and the nitrite. So now they are switched. But the reality is all we have to do is rotate this molecule and we get the same molecule again. Now you might say, well, okay, well, what if we switched, let's say, the chloride on top with one of the nitrites down below, right? To give us a structure that looked like this. Well, again, all we'd have to do is actually rotate it like that. And again, we're going to get the exact same molecule. So when you have a tetrahedral structure and you have two ligands, two different ligands and two of each, there's no way to have a geometric isomer. They're always going to be the same molecule. You'll always be able to rotate them. Now, of course, if you had only one ligand of one type and three of the other type, again, you'd always be able to rotate it in the same way. But what if we had three different ligands? So let's say we have three different ligands. This time we have these two green, the white, and then a red, which of course is going up on this tetrahedral structure. So if we had a second one that looked like that, right? So if we had a second one that looked like that, you might think, okay, well, what if we switch the white and the red, right? So if we switch the white and a red, so that would look like that. Well, all we're going to have to do is rotate it and then flip it. And you can see that we actually have the same molecule again. Okay, so let's go ahead and, well, let's switch, let's say the red and the green. Okay, so if I switch the red and the green, so that looks like that. But again, all we'd have to do is actually rotate the molecule and boom, again, we have the same molecule. So again, if you have a tetrahedral structure and you have three different types of ligands, two of one and one each of the other, again, there's no way to have a geometric isomer. You always be able to rotate them and have the same molecule. So that doesn't work either. Now, let's say we have two molecules. And so here we have, in this particular case, we have four different ligands this time. We have a red, a blue, a green, and a white. And so here obviously would be the exact same molecule. Now, what if we switch one? Let's say we switch the red and the white. Okay, so let's switch the red and the white. So there's the red and the white. We switched it. Now, is there any way to rotate it? Well, I need to get this guy down to there. So that makes them the same, but these two are different now. So if I try to get those the same, as soon as I do it again, you can see now these two are different. So these are definitely going to be geometric isomers. I'm sorry, they're going to be stereoisomers. All the connections are the same, but there is a mirror image between the two. So these aren't going to be geometric isomers. These are going to be optical isomers of one another. Okay, so you can never have a geometric isomer with a tetrahedral structure. You can have an optical isomer with a tetrahedral structure, but all four of the ligands must be different. Okay, so this is true for the amino acids, for example. Okay, let's try 38D. So this time it's square planar. So that just looks like this. We'd have our platinum as our central atom, and then all in the same plane at 90 degrees apart would be our four ligands. So one up, one down, one to the left, one to the right. Okay, so then we have two ammonia. So we'll go ammonia and ammonia. Then we have the two cyanide. Again, since the carbon is written first, that is going to be the donor atom. So remember, the cyanide, the thiocyanate, and the nitrite all can either bound to the, in the case of the cyanide, either the carbon or the nitrogen. In the case of the nitrite, the nitrogen or the single bound oxygen. And in the thiosulfate, it was either the nitrogen or the sulfate, or the sulfur, I'm sorry. Okay, so these are carbon bound. So we're going to write that like this. Okay, now we need to make another molecule that isn't the same. In other words, we can't rotate it and get the same. So the way I'm going to do that is I'm just going to put the ammonia on top and the bottom this time, and then the cyanides on either side. So now we can see that if we try to rotate this molecule, there's no way to rotate it so that the ammonias are going to be opposite one another again. So again, since the platinum is connected to the same donor atoms in both structures, we know that this thing is going to be a stereoisomer, and more specifically, it is going to be a geometric isomer. Okay, so these are geometric isomers. And if they're geometric isomers, they could either be FAC-MER or trans-cis. Now, in the case where we have a metal and then two ligands of one type and two ligands of another type, that means that this is going to be a cis-trans. Now, the trans is going to be opposite one another, and the cis is going to be on the same side. So we can see these are opposite one another. So we would call this the trans isomer, and then these are on the same side. So we're going to call this the cis isomer. Okay, looking at the ruthenium, right? So this would be the ruthenium molecule. So in this case, the greens are going to be the ammonias and the whites are going to be the bromides. So again, you can see that this is what the structure would look like, right? We have the one ammonia coming out. We have the one ammonia going back into the plane at 90 degrees. We have the other ammonia coming out towards us at 90 degrees. And again, we have the bromine coming straight down. So you can see that coming straight down, and then going back into the plane of the page would be this bromine here, which you can see going back, and this bromine coming out towards us in the plane of the page. Okay, so that would be that particular FAC isomer. We'll set that like that. And then here's the MER isomer. So in the case of the MER isomer, again, the greens are going to be the bromines. So that's going to look, I'm sorry, the greens are going to be the ammonia. So that's going to look like this. So again, you can see that we have the one coming up. We have the one coming out at 90 degrees. We have the one going straight down at 90 degrees. And then the other ones are going to be the bromine. So that would be that molecule there. Now, how do we tell the difference between the two? Well, the MER, they're all in the same plane. So in other words, if we look at this, we can see that the three ammonia are all in the same plane, right? And in fact, if we rotate the molecule like this, we can see that all the bromine are actually in the same plane as well. And so that is going to be our MER. And then in the case of the FAC, if we look at it, so here's the two ammonia, but we can see the third ammonia is in a different plane, right? So it's in a different plane. And we can see the same thing is true for the bromide. We can see that these two are in the same plane, but this is outside that plane. So it's two different planes. So that's how we have the FAC and MER isomers. And these are, again, geometric isomers. There's no mirror image of the two. Okay, next let's try number 40 from chapter 22. It says, which of the following complexes or complex ions are chiral? In addition, identify any chelate rings. So here we have a trans, cobalt, and then 4 ammonia, and 2 chlorines. So each ammonia is monodentate, each chloride is monodentate. So there's a total of 6. So that's going to make 6 coordinate covalent bonds, which means we're going to have an octahedral structure. So we're going to have our cobalt is our central atom. Again, we'll have one up, one down in the same plane of the paper. Then again, in this equatorial plane, we're going to have 4 in the square planar. So we're going to have one going back into the paper, one coming out of the paper at 90-degree angles, and again, one going back at 90 degrees, one coming out of the paper at 90 degrees. And so there's our octahedral structure. Now it's trans. Now remember that for trans, they are on opposite sides. So we have just 2. So those are the ones we're going to focus on. So they're going to be on opposite sides. So we'll put one here and we'll put one here. Okay. Then the other is going to go here. The other is going to go here. And then the other ammonia over here and the other ammonia over here. So there is our trans tetraamine dichloro cobalt 2 ion, complex ion. Okay, so it wants to know, is it chiral? Well, if it's chiral, it will have no plane of symmetry. But as we can clearly see with this particular complex ion, if we split it right down the middle here like this, right, we can see that we have a plane of symmetry. So there's our plane of symmetry. So that means that this is not chiral, and we would say that this compound is actually achiral. Okay. And chelate ring. Well, chelate rings can only be formed by polydentate ligands. Since these are all monodentate, there's going to be no chelate rings. Okay, next let's look at this isomer here. So this is a cis, and then we have the ethylene diamine, which is a bidentate ligand. So there's two of them, so that's going to be 4 coordinate covalent bonds. And then we have 2 ammonia, okay, and they are going to be monodentate ligands. So that's 6 coordinate covalent bonds. So we're going to need then to draw the central atom, which is our chromium, and then again, 1 up, 1 down, 1 going back into the page and 1 coming out at 90 degrees, 1 going back into the page and 1 coming out at 90 degrees. And so there is our structure. Now this time it's cis, so that means they're on the same side. So let's draw both of these ammonia on the same side of the molecule. And then we have this ethylene diamine. Now remember, the ethylene diamine molecule looks like this, right? We have a nitrogen, and the nitrogen has a lone pair. It has 2 hydrogens coming off of it, and then it's bound to another carbon, which has 2 hydrogens coming off of it, which is bound to another carbon, which has 2 hydrogens coming off of it, which is bound to another nitrogen with a lone pair and 2 hydrogens coming off of it. And remember, for these bidentate ligands, we have to have at least 4 atoms between the lone pair. So there's the lone pair, 1, 2, 3, 4. So that's what allows this to be a polydentate ligand, specifically in this case, a bidentate ligand. And so here would be our metal, and then the coordinate covalent bonds are going to form with those lone pairs. Now, instead of writing this whole thing out like that, which would be very cumbersome, what we're going to do is we're just going to write the donor atoms and then a line connecting the 2 donor atoms. So in this case, we would have the nitrogen, the 2 donor atoms being connected, and then a nitrogen, and the 2 donor atoms being connected. Now, in this case, we want to know, is it chiral or achiral? So the question is there a plane of symmetry? Well, we certainly can't cut it down this way, right? We can't cut it down this way. This side's definitely different than the other. You might think that we could cut it right along this axis right here. However, when we look at it, okay, this side is the same as this side. But when we look at this one is coming out while this one is going back. So they are not symmetric. They're not mirror images of one another. So again, there is no plane of symmetry, right? So there's no plane of symmetry. So this would be chiral. So that would be a chiral molecule. Now, next it wants to know, is there any chelate rings? Well, a chelate ring is basically forming a ring, right? So we have our central atom, and then bounded to the nitrogen, which is eventually bound to the other nitrogen, which then again is bound to the chromium. So here you can see we have this ring of atoms, and so this would be considered to be a chelate ring. So we see it there, but we also see another one here, right? So here's a second chelate ring on this particular complex ion. Now we have so we have the structure of this one, this molecule here, this complex ion. And we can see that it's octahedral, right? All 4 are 90 degrees apart from one another, no matter which way you turn it. So we can see that it's octahedral. So I could see if we hold it like this is kind of the way this is represented. We have the one ammonia going down and behind the page. We have the other ammonia coming up and out of the page, right? It's either coming down and out of the page. Then we have this nitrogen going up, and it's being connected to the one going back behind, right? It's going back behind the page. And then we have this nitrogen, which is coming straight down. And then it's connected to the other nitrogen, which is the one coming out and towards us. Again, you can see that's coming out and towards us. Now, the question is, can you see the plane of image? Is there a plane of image? Well, if we rotate the molecule this way, right, and we try to slice the molecule straight down the middle here, you can see that there is no way. This one's on the wrong side of this one, so there's no plane of symmetry there. You can't slice it this way. If you try to slice it this way, we can see that this is definitely different than this side over here. You could try to slice it, let's see, we could try to slice it this way, but this one's on top, this one's on the bottom, and again, you can see these two are different as well. So you can see that there's no plane of symmetry with this molecule. There's no way to cut it in half. To get two sides that are exactly the same as one another. Okay, next let's try number 42 from chapter 22. It says, draw all possible geometric isomers and optical isomers for each of the following complexes or complex ions, and label the geometric isomer as cis-trans, or if it would happen to be FAC-MER. Now, we're not going to draw all the possible geometric isomers, but we will draw a set of each. So let's start with looking at the actual complex ion. So we have the palladium as our central atom. We have a bromide, which is monodentate. The glycinate, which is bidentate. There's two of them. So that's going to be 4 coordinate covalent bonds. And then the ammonia, which is monodentate. So we have 1, 4, and 1 that's 6. So again, we're going to have an octahedral structure. So we'll have our central palladium atom, and then 1 up, 1 down, and that axial positions. And then in the equatorial plane, again, we're going to have a square planar. So we're going to have a bond going back behind the page at 90 degrees to the one coming out of the page. And again, one going back at 90 degrees and one coming out of the page at 90 degrees. And since again, these are isomers, let's just draw the other structure real quick. And again, one going back at 90, one coming out at 90 degrees, one going back at 90, and one coming out at 90 degrees. Okay, so let's start. So I have a bromine and ammonia. So let's just put those at top and bottom for now. And then we have the 2 glycinate. Well, again, the glycinate has the structure. It has a nitrogen with a lone pair, and then it has 2 hydrogens coming off of it. It is connected to another carbon, which has 2 hydrogens coming off of it. That is then bound to another carbon, and that carbon has 2 oxygens. One is double bound, and the other is a single bound oxygen. And so again, of course, this is an ion. So it has a charge of -1. And again, the metal is going to sit right here, and it's going to use a lone pair off of the singly bound oxygen and that of the nitrogen to form its 2 coordinate covalent bonds. And again, instead of having to draw that entire structure like that, we're just going to represent this by drawing the donor atoms and drawing a line between the 2 donor atoms. Okay. Okay, so let's do this then. So this is going to be the nitrogen and the oxygen. And let's say the nitrogen and the oxygen. Okay, so there's one isomer. So now we can make another isomer. Let's go, this time let's put the bromine and the ammonia here. And then let's put the nitrogen and oxygen and nitrogen and oxygen. Okay, so there is the two different structures. Now, in this case, you could see that there is absolutely no way to rotate them to get the same molecule. So they're definitely isomers. They are not mirror images of one another. So they're not, so they're stereoisomers since all the connections are the same. They're not mirror images, so they're not optical isomers. That means they're geometric isomers. And if they are geometric isomers, we're going to either have to label them as cis-trans or FAC-MER. In this case, they will be cis-trans. Since if it's going to be FAC-MER, it has to have 3 ligands of the same type and then another 3 ligands of a different type. In this case, we have a total of 3 different ligands. So this thing is going to be cis-trans. So looking at the nitrites, I can see these nitrites are on either side of the central atom. So this is going to be our trans. And these two are on the same side. So this is going to be our cis. And these two isomers are going to be geometric isomers. Okay, next, and you can imagine there's actually other ways that we can arrange this and actually have different isomers as well. So next, let's look at see if we can get an optical isomer. Now, an optical isomer, of course, is going to have a mirror image. So let's look at this one here. So let's do this, and let's see if there is a mirror image of this isomer, and if it's different, which would make it an isomer. So we'd have our central palladium atom, would have one up, one down. At 90 degrees, a bromine going back behind the page, and at 90 degrees, one coming out of the page. That would be our ammonia. And then again, 90 degrees going back into the page. And then at 90 degrees, one coming out of the page. And this time, messed up, right? So this would be the bromine. So this is the bromide here. This would be the ammonia, okay, if this is a mirror image. And then our nitrogen would be on top, and then going in a mirror image, this would actually be the oxygen, okay? And then this one here would be the nitrogen, and again, going back here, again, would be the oxygen, okay? So there is our optical isomers. And again, there's no way to rotate this. So to rotate this, if I rotated it 180 degrees, right? 180 degrees would put this bromine here and put this ammonia here. Okay. That wouldn't work because they're not the same. So what else can we do? So if I rotated that and I did that, right, that would look like this. So this would be that first rotation. So let's just look and see what happens. So this would be the first rotation. And again, what we're doing is we're rotating it 180 degrees along this axis. And that's what's given us this guy here, right? So that would bring him over to here. That would bring him to here. Now the nitrogen is going to stay the same, right? It's going to be on top. But then it's going to bring it to here, okay? So that would be to here. So this would be connected to here. And then there's this nitrogen. And that's going to bring this one back to here. So this one would go like that. Okay, but the problem is that these two are still not in the same position. So now we're going to have to rotate the molecule this way, right? So now we're going to rotate along this axis. We're going to rotate it 180 degrees again, and that will give us, let's say, this structure here. So again, we have our central palladium. Okay, so this time again, we're going to rotate it this way. So that is going to put the bromine here and the ammonia here. Now let's look at this one. So that's going to flip this guy to here. Okay. And then this oxygen now is going to be here. So these two are connected. Then this nitrogen would be flipped down to here. And then this oxygen is going to be flipped back to here. So you can see now that this is not the same. This nitrogen is supposed to be connected to here, but it's connected to the one down here. So we can see that these two are not the same. And therefore, we would call these our optical isomers. Okay, so those are the optical isomers. Now, we could also look at this one too, and we could determine whether or not they're chiral or achiral. In this particular case, for this complex ion, we have a plane of symmetry going right down through the middle of the molecule. So this thing would be achiral. In this particular case, we can't go that way because these are different. We couldn't go that way because they're different. Basically, there's no plane of symmetry for this one, and the same thing is going to be true for this guy. So in both of these cases, they would be chiral. And as far as chelate rings, well, here would be one chelate ring. Here would be a second chelate ring. And again, we can see there would be a chelate ring here, a chelate ring here, a chelate ring here, and a chelate ring here. Okay, next let's look at this first isomer here. And so basically what you can see is that in this plane, okay, so in this plane here, we have the oxygen going back connected to the nitrogen, which is now coming on this one, that's coming out towards us. This one's coming out, which is the nitrogen, and then we have this one, which is going back, which is the oxygen. So then when we rotate this thing, so it's basically on the plane, you can see that the bromine, is going up. And the ammonia, which is represented by this, the ammonia is coming down. Okay. Okay, so there's that particular isomer. Now, the point here is the plane of symmetry. You can see that if we slice this molecule straight down this middle right here, you can see that we have that plane of symmetry. They are the same on both sides. That would be a mirror image along that plane of symmetry. So therefore, this molecule would be achiral. Next, we have the other two isomers. Okay, so this isomer here would look like this, right? So again, we have the bromine going back into the page. We have the ammonia coming out towards us. We have the nitrogen on top, and it's being bound to the metal atom from behind at 90 degrees. And then on this side coming down, we have the nitrogen, right? So we have the nitrogen coming down, and then again coming out at 90 degrees to the left, we have the oxygen bound on it. So that would be that isomer right there. Okay, so there's that isomer. Next, let's look at the other isomer. So this would be the mirror image, of course. So here you can see that they are clearly mirror images of one another, right? They are both going up and they're both going down on the bottoms. Okay, so they are clearly mirror images of one another. Okay, so that, of course, makes them optical isomers. With both of these, you can see there's no plane of symmetry. I can't slice it this way and have the same on both sides. I can't slice it down this way. Again, you can see this one's up, this ring's up, this ring is down. So there is no plane of symmetry for this molecule. So there's no way to rotate this that we could slice this thing in half and have the same molecule. Now the question is, are they the same molecule? Okay, well, first thing we would do is we could rotate it. So if we're following this here, right, the first thing we did was we rotated it along this axis to go like that. So 180 degrees, we rotated it. So now you can see that we still have an issue though, right? The ammonia is on the wrong side from the bromine. So now we're going to rotate it this way. Okay, whoops, I'm sorry. We're going to rotate it this way now along this axis so that we get the two the same. So now you can see that we have the bromine and the ammonia are the same. But when you look at the chelate rings, you'll notice that they're not the same, right? So if we look at the chelate rings, we could see on this molecule, it's coming up, and then it's coming to the one that's coming out towards us. And on this chelate ring, it's going up, but it's going to the one behind, the one away from us. So if we look at these two things, okay, let's get this right orientation. So if we look at these two, you can see that the chelate rings, one's going up when the other one's going down, and the other one's up when the other one is down. So they are not the same molecule. There's no way to rotate them. So they are for sure then optical isomers. They have a mirror image, right? They have a mirror image, but there's no way to rotate them so that they are the same molecule.